Hello everyone, my name is Shruti along with my teammate Raviteja Kothuru. We are from Team 5 in the AI 590 Capstone course at the University of San Diego. Today we are excited to present our capstone project, Automated Coral Health Detection using Deep Learning. We have developed an AI system that addresses one of the most pressing environmental challenges of our time, the rapid decline of coral reef ecosystem. Working under the guidance of Dr. Zahid Hussain Wani, we have created technology that can transform how conservation organizations monitor and protect these vital marine habitats. So, we developed this project considering all the feedback from our professor throughout this course. Let's start with why this matters. Coral reefs are extraordinary ecosystems. They support 25% of all marine life while covering less than 1% of the ocean floor. They provide coastal protection, support fisheries worth billions, and sustain tourism industries worldwide. But they are in crisis. Climate change, ocean warming, and pollution have triggered massive bleaching events. The problem is that we lack the tools to monitor reefs at the scale needed for effective conservation. Current methods rely on marine biologists manually annotating thousands of underwater images, a process that's actually slow, expensive, and simply doesn't scale. This manual bottleneck means conservation teams often get data months after surveys are conducted, delaying critical interventions. When a reef starts bleaching, we need real time data, not retrospective analysis. So, our solution is an end to end AI system that automates coral health assessment. Here's how it works. First, underwater images are collected from reef sites using divers, underwater drones, or fixed cameras. These images are fed into our deep learning models, which automatically classifies coral health and detects specific stresses. The system generates real time health assessment, which conservation teams can use to implement targeted interventions. The key innovation here is scale. Where manual methods might process 50 images per hour, our system can analyze thousands in the same time frame. This transformation from months to hour isn't just about speed, it's about changing conservation from reactive to proactive. Instead of responding to damage that's already occurred, team can identify problems early and prevent catastrophic loss. So now let's talk about the technical approach. We use the Coral Condition Dataset, a benchmark dataset containing over 39,044 professionally annotated underwater images. Each image is labeled with a health status like healthy, compromised, dead, or rubble, and the specific stresses like disease, predation, and physical damage. Here you can see what these different states look like. Healthy show vibrant colors and complex structures. Compromised corals display partial bleaching, and dead corals are pale with algae growth, and rubble consists of broken and fragments likewise. So we choose the EfficientNet V2S architecture for this excellent performance of accuracy and efficiency. The real innovation was our two-phase training strategy. First, we leveraged pre-trained weights from ImageNet, then fine-tuned specifically for coral imagery. We validated against the classical models to ensure robustness. Diving a bit deeper into the architecture, we start with pre-processed underwater images resized to 384 by 384 pixels. These feed into the EfficientNet V2S backbone, which has been pre-trained on millions of general images but understands universal visual concepts like edges, textures, and shapes. To this, we added a custom classification head with dense layers, batch normalization, and dropout for regularization. The output provides both health classification and confidence scores. So, one fascinating discovery was that deep learning embeddings, the high dimensional representation our model creates, shows nearly perfect linear separability across health categories. This means that once images are processed through our neural network, even simple linear models can classify them with extraordinary accuracy. Next, my teammate Ravi would continue.
Thank you, Shruti. Now, let me walk you through our results. Our EfficientNet V2S model achieved 89.98% validation accuracy and an 89.23% macro F1 score. The F1 score is particularly important because it shows balanced performance across all categories, not just the common ones. The 100 times speed improvement is transformative for conservation work. But what really impressed us was the linear separability discovery. When we extracted features from our model, and fed them to a simple logistic regression classifier, it achieved 98.83% accuracy. This tells us our deep learning model creates an exceptionally clean representation space. So this performance is not just a laboratory result, it translates to practical impact. Conservation teams can now monitor reef areas that were previously impossible to assess comprehensively. Moving forward with model deployment methodology, the model processes the images in just 0.2 seconds and returns with the detailed results. It can be classified as healthy with 94% confidence with minimal probabilities for other states. This same efficiency scales to batch processing. We can analyze thousands of images from an entire reef survey in minutes. Results export directly to conservation dashboards and GIS systems for mapping. The lightweight architecture also supports deployment on edge devices and autonomous underwater vehicles, meaning which we can process data right at the source without needing cloud connectivity. As you can see, this is not just theoretical, it's ready for real world application. Moving forward with applications and impact of this one, let's talk about who benefits from this technology generally. For conservation organizations, it enables rapid, scalable assessment across multiple sites simultaneously, optimizing limited conservation dollars. Research institutions gain unprecedented datasets for climate impact studies. Government agencies get objective, standardized data for environmental compliance and policy planning. And the tourism industry can implement sustainable reef management, ensuring long-term viability of marine tourism. Most importantly, our work directly contributes to United Nations Sustainable Development Goal number 14, which is life below water. We are not just building technology, we are supporting global conservation efforts. Moving forward, let's discuss with the future development. So we have a clear development roadmap here. In the short term, for the first 1 to 3 months, we are focusing on hyperparameter optimization, experimenting with vision transformers, and developing production APIs with Docker containers. Coming to the medium term part, we'll expand to multi-region datasets to improve generalization, deploy on mobile and edge devices, and integrate with autonomous underwater vehicles for real-time analysis during surveys. The long-term vision will include a global reef health dashboard, climate impact forecasting models, and analytics to calculate conservation return on investment. Our production readiness package includes containerized services, cloud templates, and comprehensive documentation, everything needed for seamless integration into existing workflows. In final conclusion, we have developed an AI system that achieves approximately 90% accuracy in coral health classification. This accelerates analysis by 100 times compared to manual methods and creates production-ready technology for immediate conservation use. This work demonstrates that deep learning can transform environmental monitoring, making large-scale ecosystem assessment not just possible, but practical. By automating what was previously manual labor, we free conservation experts to focus on intervention rather than annotation. Our technology represents a scalable solution to one of marine conservation's biggest bottlenecks, directly contributing to the preservation of these vital ecosystems for future generations. Lastly, thank you for your attention and thank you for providing us this opportunity to share our project with you.
Thanks a lot for this opportunity. Thanks, everyone.